stability and instability in Kerr-anti-de black holes.
Sorry, yeah. Thanks for this introduction, and thanks for the invitation, and again also for the organizing this very nice conference. So it's funny. My title is very similar to Mario's title, but and the math. I mean, there will be some similarities. Okay. Okay, so I'm going to present linear gravitational stability and instability results for Kerr-anti-de Sitter spacetimes. So our object of study is going to be spacetimes mg, where m, okay, okay, that's bad, where m is a four-dimensional manifold and g is a Lorentzian metric on m. And we will consider spacetime which satisfy the Einstein vacuum equations, which g of g is equal to lambda g, where lambda is a cosmological constant. And in this talk, we will assume that lambda is strictly negative. Okay. So the prime example of such a spacetime is anti-de Sitter space, where m is r times r3, and where the anti-de Sitter metric reads minus delta over r squared dt squared plus r squared over delta dr squared plus r squared times the unit Euclidean metric on the two sphere. Okay. So here delta is the famous delta that Elena talked about and Mihalis also. So, but it's this one is much more simple. It's so it's a fourth order polynomial in R. With leading coefficient k squared, where k is a renormalization of the cosmological constant. So I should say that anti-de Sitter space is a homogeneous isotropic solution of the Einstein equations, and you note that if you do k is equal to 0 in that expression, you find back the Minkowski metric in spherical symmetry. Okay. So you can define a new radial coordinate r star by such that its derivative with respect to r is r squared over delta, and since r squared over delta it's like 1 over r squared when r goes to infinity, this is integrable. So in general this r star will always have a limit at infinity, and you can choose for example this limit to be 0. Okay, why not? So if you use this new radial coordinates, you can rewrite the anti-de Sitter metric as follows, and where I factorize here the metric by a factor delta over r squared. Okay, so now it makes a factor 1 over w appear, and where w is delta over r4, and when r goes to infinity, delta over r4 goes to k squared, okay, which is non-zero. So subsequently, you can show that you can extend smoothly the function 1 over w, this function, at r is equal to 0 at infinity. Okay. So therefore, if you multiply the anti-de Sitter metric with the conformal factor r squared over delta, then you obtain a metric which is defined on a larger manifold, which includes a bound and is regular, and which includes a boundary at r star is equal to 0. Okay. So on this boundary at r star is equal to 0, the induced metric is minus dt squared plus this is 1 over k squared times the unit Euclidean metric on the two sphere. Okay, so the induced metric is exactly the metric of the Lorentzian cylinder on r times s2. Okay. So I could have, I multiplied with the conformal factor r squared over delta, but I could have also multiplied this with a positive function of the variable t, theta, and phi, and this would have I would have had another. This would have give me another metric, which would be conformal to this one. So this procedure defines you. Defines you in a somehow unique way. Only the conformal metric of the induced metric at infinity. Okay. Now, if now I can include what I can do, I can include a factor minus 2m in my polynomial delta. So here I take m strictly positive, and so this is still a solution to the Einstein equation. Which is stationary and spherically symmetric. So it's called and it's known as the Schwarzschild-anti-de Sitter metric, and it corresponds physically as putting a Schwarzschild black hole of mass m inside the anti-de Sitter spacetime. Okay, so now this polynomial delta has a strictly positive root. So, and I will choose to, well, we will restrict ourselves to the domain to outside of the. So this root is called this root is the black hole radius, and we will restrict to values of R outside of the black hole radius. Okay. So in this context, you can still define a coordinate, a new radial coordinate R star, which corresponds to a tortoise coordinate, because as you can check with this definition, R star goes to minus infinity when R goes to R plus. To the black hole radius. Okay, using this radial coordinate R star, you can still show that the Schwarzschild-anti-de Sitter metric conformally embeds into a larger manifold where the conformal induced metric at infinity is still the Lorentzian cylinder metric on R times S2. Okay, so now you can complexify even more your polynomial delta and add a factor a squared here. You still have a solution to the Einstein equation, which is stationary and axis symmetric, and it corresponds. So it's called the Kerr-anti-de Sitter spacetime, and it corresponds physically to putting a rotating Kerr black hole inside an anti-de Sitter manifold. You can still define a tortoise-like coordinate R star, and you can still show that doing a similar procedure that you obtain you can embed your manifold conformally into a larger manifold which has a boundary at infinity, and the induced metric on this boundary is conformal to the Lorentzian cylinder metric. Okay. So as for the classical Kerr spacetimes, you can attach two null boundaries, the past and the future event horizon to these spacetime regions that I presented, and you obtain And here I show you the Penrose diagram of such a spacetime. Okay, and I forgot to say that the metric on the induced boundary is Lorentzian. Therefore, the boundary is time-like. This is a time-like boundary. Okay, so the Kerr-anti-de Sitter spacetime, they are far from being the only solutions to the Einstein equations with negative cosmological constant. So indeed, Friedrich proved that there is a well-posed initial boundary value problem. So that if you give yourself admissible initial data, then there exists a unique solution to the Einstein cosmological equations with prescribed boundary condition at infinity. And the boundary condition at infinity is, in fact, the induced conformal metric at infinity. So in the case of the Kerr-anti-de Sitter spacetime, these were the Lorentzian cylinder, the conformal class of the Lorentzian cylinder metric. Okay, so let me highlight some elements of the proof of Friedrich, which will be relevant for the rest of the talk. So Friedrich, the main dynamical quantity that Friedrich uses to prove his result is the Weil tensor, which is the traceless part of the Riemann curvature tensor, and for space-time which satisfy the Einstein equation reads like this. You can show using that your space-time satisfy the Einstein vacuum equations and the second Bianchi identities. You can show that the Weil curvature tensor satisfies the so-called Bianchi equation, which is that the space-time divergence of your tensor is 0. So this you can see as a system of symmetric hyperbolic equations, which okay, I mean, if you fix the metric, it's a linear system of symmetric hyperbolic equation, and for which you can construct solution if you prescribe boundary conditions for the Weil tensor. Okay, so for instance, one possible choice is to prescribe all these components of the Weil tensor, where so n here is the normal to the boundary, and ijk here denotes a tangent indices to the boundary. Okay, but actually it turns out you can show that using the Einstein equations and the conformal property of the Weil tensor, you can show that on the boundary this quantity actually coincides with the Coton tensor of the induced metric of the induced conformal metric on the boundary. So the Coton tensor is a conformal invariant, and for example, if you take the Lorentzian cylinder metric, you can show that the Coton tensor vanishes. So which gives you homogeneous Dirichlet boundary conditions for some of the components of the Weil tensor. Bref. So you've got I mean, Friedrich showed you that you have a well-posed initial boundary value problems. You have some stationary solutions, which are the family of the Kerr-anti-de Sitter solutions. So a natural solution is if you perturb initially the initial data at time t is equal to 0 of your solution, do you stay close to the Kerr-anti-de Sitter solution, are they stable, and even are they asymptotically stable? Okay. So I will just focus on the first, obviously the first thing you want to do is to investigate the linear stability, of this spacetime. So this is, I will only talk about linear stability results. So the plan of my talk is to present you two types of results. So the first result that I'm going to present is on Schwarzschild anti-de Sitter. So these are where we establish a weak linear stability result. So this is joint work. This is all joint work with Gustav Holzhegel. And the second result, second type of result that I want to present you is on the Kerr-ADS spacetime, and I want to present you a mode stability result, which is also joint with Gustav Holzhegel, and in the direction of instability result, which is a result of myself. Okay, let's start with the Schwarzschild case. So the result that we have is the following. So we show that roughly we show that all the solution to the linearized Einstein equations around the Schwarzschild-anti-de Sitter metric, where you fix with the linearized boundary condition which come from the fixing the conformal class of the induced metric at infinity. So we show that all the solutions are bounded and have a decay in time as a 1/log. And we also show that this decay rate is sharp. Okay. So here I've said time, but I will choose to work with the advanced time t plus r star, which is not not real time. And I will also work with the retarded time t minus r star. Okay, so this result is as you know from the previous talks, this result can only be true up to pure gauge solutions and linearized Kerr-radius solutions. So this is, you should understand it like this. Second remark is that, okay, this result is based on previous work of Jacques Smolivichy and Olsegel for the wave that were obtained for the wave equation. Okay, and let me say, okay, and last remark. So this is a weak result because the decay is only in 1/log in time, which is very slow. If you saw this is not polynomial. This is very slow, and this might rather be the sign of an instability at the nonlinear level, because you won't be. I mean, it seems it will be hard to close a nonlinear stability proof with this type of decay rate. So in that direction, there are nice simulation by Pau, Frick-Ras, and Rossi, and you will also hear about the nonlinear story in the talk of Yorgos this afternoon. So let me now go to the how do we prove this result. So I will first show you that all solutions decay, and then I will show you the lower bound, which is that this decay rate is sharp. Okay, so if you take a metric perturbation h, what you can do is you can look at the linearized your linearized Weil tensor at the Schwarzschild-anti-de Sitter metric in the direction of h, and you can contract this linearized Weil tensor with null direction. So dv and what? dv and du, which corresponds to the coordinate vector field in the UV coordinates, and you can, if you want, but that's not necessarily mandatory, but you can contract with a complex vector field built out of the spherically tangent, the vector fields d theta and d phi. Okay, so these are the well-known Tucholsky quantities, which I will note alpha plus 2 and minus 2, but they correspond to alpha and alpha bar of the talk of Marius, and correspond to the psi 0 and psi 4 of the talk of Dietrich, I think. So well, anyway, so if you remember my discussion on the proof of Friedrich, your Weil tensor satisfied the Bianchi equations. So if using this, you can show that the Tucholsky quantities satisfy two wave equations, which remarkably are decoupled from the other metric perturbations. So these are the well-known Tukowski equations, which are of wave type. So here I denoted by this L plus and minus two angular spherical operators, which you should think of as a Laplacian on the two sphere. And in this talk, I will silently project everything onto the spherical harmonics for this Laplacian. So you can think of this L as being only the eigenvalue of L, which is L plus 1, with small l larger than 2, because the Tukowski quantities, which is related to the fact that the Tukowski quantities alpha plus and minus 2, they are spin 2 weighted functions. Okay, so now if you remember what I've said for from the proof of Friedrich's results, you can the fact that you had homogeneous Dirichlet conditions for some of the Weil some of the components of the Weil curvature tensor. This translates in the fact that you can obtain coupled Dirichlet and Neumann boundary conditions, which couple the two Tukowski quantities alpha plus and minus 2. Also, by the way, this asterisk here denotes for me in the talk the complex conjugation. Okay. So one thing. So one of the main difficulty of the Tukowski equation is that there's no so far a natural energy associated to this wave equation, because it contains first order derivatives, as Marius pointed in the previous talk. So what you do, and you do exactly what not exactly, because but you do something which is very similar to what Marius said, which is that if you commute 2 times this equation with du derivatives, and if you commute this equation 2 times with dv derivatives, remarkably, you obtain for this 2 derivative of du of alpha plus 2 and 2 derivative in the v direction of alpha minus 2, you obtain this wave type equation, which is remarkably which is decoupled fully, and which doesn't have first order term, which doesn't conserve first order term. So for which you will have conserved energy quantity. So this is commuting 2 times. This is the Chandrasekhar. This is called the Chandrasekhar transformation, and this is the fundamental remark that was done by Michaelis, Dafermo, Solsegel, and Roniansky in the proof of the linear stability of Schwarzschild spacetime. Okay, so in Schwarzschild ADS, it works the same. Okay. Now you've got a wave equation. That's very nice. And you wonder what are the boundary conditions that you get for the Reggie-Wheeler quantity psi plus and minus 2. Okay, so if you use the Tukowski equations and the boundary conditions that you have for alpha plus and minus 2, remember the coupled Dirichlet and Neumann boundary condition, then you get this coupled Dirichlet condition for psi plus and minus 2. And you've got this coupled Neumann boundary condition for psi plus and minus 2 together, which is coupled to the values on the boundary of your quantities alpha plus and minus 2. So that's unfortunate, because we.
Is there a way to write the boundary condition all in terms of psi plus and minus somehow to use the identities?
So this is unfortunate, and Marius has a very good idea, which is that can we? So it's unfortunate that you've got a decoupled wave equation, but your boundary conditions are coupled. So it's sad. But as Marius, following Marius' idea, you can use. So so if you have solutions to the Tucholsky equation, alpha plus and minus 2. If you derive 2 times in the u direction, but then you derive 2 times in the v direction, using the Tucholsky equation, you can show that you've got some elliptic operator plus the time derivative. Okay, so this is quite general, and same for the alpha minus 2 case. So if you sum these two identities, using that alpha plus 2 minus alpha minus 2 goes to 0 at the boundary, then you have that the sum of alpha plus 2 and alpha minus 2, this thing, is the sum of these two things modulo inverting this angular operator, four-order angular operator. I've said that you should think of it as only as a positive function, L plus 1, so well, a priori that's fine. Okay, and so in short, you can replace this. You can replace the boundary the alpha plus and minus 2 in these boundary conditions by this. Okay, so it looks a bit ugly, and the thing and one of the thing is that it still couples the plus and minus 2 Reggie-Wheeler quantities. Okay, so what you can do is you can define two new Reggie-Wheeler quantity, psi d and psi r. Psi d being the difference of the psi plus and minus 2, and psi r being the sum with a correction term. Okay, so these two Reggie-Wheeler quantities, they still satisfy the Reggie-Wheeler equation, and so the first boundary condition becomes Dirichlet boundary conditions for psi d, and the last boundary condition decouples from psi d and becomes this boundary condition for psi r. And which is again, so the normal derivative of psi r is equal to tangential derivative on the boundary of psi r modulo inverting a fourth-order elliptic operator. Okay, so this is the reason why I call this psi r like Robin, because this is a Robin type boundary condition. If you forget, that's I mean these are well, this is funny Robin boundary condition. Okay, so now we've got a fully decoupled problem for each of your Reggie-Wheeler quantity, the Dirichlet and the Robin Reggie-Wheeler quantity. So, and you've got a wave equation for which you'll hope to. This is the Dirichlet and Robin, and you've got a wave equation for which you'll hope to prove energy boundedness. So how do you do that? Well, I just do it in a very elementary way. So you take your Reggie-Wheeler equation and you multiply by, you want to multiply it with dt psi, and you integrate in a spacetime domain. So we'll integrate in that region between two hypersurfaces. V is equal to constant. So if you do that, I won't do the computation, but you can do from here. What you get is that integrating by part, what you get is that there is so you've got an integral at v is equal to v1, so which we'll call the energy of psi, which is equal to a positive flux on the horizon plus a flux at infinity here, plus the energy at v is equal to v2. Okay, so now if your psi satisfies the Dirichlet boundary condition, this dt of psi, it's a tangential derivative on the boundary, it is 0. Okay, so you don't have, there's no flux through infinity. And what you have is that the energy of at time on v is equal to v2 is less than the energy at v is equal to v1. Okay. Now, if you have your regular quantity which satisfies your funny Robin boundary condition, what can you do? So you look at the flux at infinity, and you replace the normal derivative of psi by its value, and you can notice that in fact this is an exact derivative in time. So you can integrate. Your integral here is in fact the sum of a boundary term here minus a boundary term here, and the boundary term it's this thing. Okay, so the idea is that if you modify your energy and you add this boundary term at infinity here and here in the energy, then you obtain that your energy you obtain an energy which decays. So you're happy. Okay, so now let's take a closer look at what this energy is. So here you've got a u derivative of psi squared. So this is positive. You've got here these are squares, and this is all positive. So everything is positive. But this potential here, so it's LL plus 1 minus 6m over r. So is it positive? So in the Schwarzschild case, where r the black hole radius is 2m, so this potential L minus 6m over r is since this capital L is L plus 1 with small l greater than 2, this is always greater than 6, and this is always greater than 6 minus 6m over 2m, which is always greater than 3. In short, it's positive. So this is a coercive energy. Okay, that's nice. In the Schwarzschild case, it's quite different, because in fact, if you fix the mass and if you let the cosmological constant go to infinity, then your Schwarzschild horizon radius goes to 0. So this potential will become negative close to the horizon. So your energy might not be coerced. So the trick is that you can use a Hardy type idea, and you can twist your energy by introducing a function f, and you can rewrite your energy like this. So one very funny thing is that when you do this will exactly absorb one of the positive term at infinity that you had. Okay, so somehow you needed to have this term on the boundary to have it seems that this is very useful to have a coercive energy quantity. Okay. When did I start?
50.
Okay. Thanks. Okay, so you've got a bounded decreasing coercive energy, so that you can hope to prove some boundedness statement. Moreover, so there's it's a general idea using that I mean you're losing some energy through the horizon, so you can exploit this, so you do the same thing as for your for the energy quantity, but you multiply with radial derivative of psi and an exponential weight in R. And you can integrate by part many times. You might also have to do some Fourier analysis. And but in the end, you'll be able to show that the integral of the energy. I mean, okay, this time it's very important that it's your solution projected onto the spherical modes. So for each mode, the integral of the energy is controlled by the initial energy times a factor which depends on the angular frequency small l. Okay. So using this for each angular mode psi ml, you can show that you've got exponential decay of the energy. Exponential decay, but with a rate which is I mean, when your angular frequency goes to infinity, this goes to 0. Sorry, this goes to 0. So in fact, if you want a decay rate which is uniform in L, here you can do no better than 1, which is simply the energy boundedness that you had before. So no gain. Okay, but the idea is that if you're okay with losing some angular derivatives, so you can put a small angular frequency in your energy. So you can add 1 over L to the power 2p, with p the power how many angular derivatives you're okay with losing. Then so it's a small exercise. You can show that this thing is uniformly in L bounded by 1 over log v to the power 2p. So 2p, and then if you sum your spherical harmonics, then you get that the energy of a general solution to the regular equation then decays as 1 over log v to the power 2p, with p the number of derivatives, your angular derivatives, you want to lose. Okay. So this is for the regular equation. Now you can integrate. So now you play a game which is similar to what Marius did. So you've got estimates for the regular equation. So you can integrate 2 times integrate the Chandrasekhar transformation, which are like transport equation, and then you can integrate the whole system of null structure equation to get a result for a metric perturbation. But I won't show this because I want to do other things. So now how do you prove that this result is sharp? Okay, so how do you prove that this decay rate is sharp? So the idea is that again, an idea of Jacques and Holzhegel. The idea is that you try to construct the solutions which exactly do not decay. That is, you purely oscillating, a pure mode. You try to construct a pure mode solution. Okay, so you take this ansatz and you plug that ansatz in the regular equation. So this gives you equations which are eigenvalue equations, where the eigenvalue is your oscillating frequency omega squared. Okay, so if you're trying to look for eigenvalue, one very natural thing is to work on the compact domain, because if you want to apply a spectral theorem, that's very convenient. So what you can do is you can truncate your domain on so you can truncate your domain on a fix at a fixed radius, and at this radius r, you can impose, for instance, a Dirichlet Dirichlet boundary condition. Okay. So you've got two eigenvalue problems. One for the regular Dirichlet quantities where on the boundary at infinity you have a Dirichlet boundary condition, and you have the eigenvalue problem which comes from the Robin regular problem where on the boundary at infinity you have this funny boundary condition where here the eigenvalue is inside the boundary condition also. Okay, so how do you construct solutions to these eigenvalue problems? So the idea, I mean, a very elementary way to do it is to consider a minimization problem, and to try to minimize the following Rayleigh quotient. Okay, and so first I say it in the Dirichlet case. So to minimize the following Rayleigh quotient over all functions which vanish at the boundary. Okay, and so I mean you can do it because you're on a compact domain, and you obtain this infimum is a minimum, and so it gives you the fundamental frequency and the fundamental associated eigenfunction psi. Okay, so if you wonder in the Robin case, how can you do this? But it's quite funny. The idea is that you can twist your Rayleigh equation by including the one boundary term on the numerator and one other boundary term. Well, that's kind of classical for Robin conditions, but one other boundary terms on the denominator, which is a bit exotic. Okay, and you can minimize this for all solutions. And here it should be H1 not at the other boundary condition, but not at infinity. Okay. So note that this is very naive. In fact, that's not exactly the way we do it. You can prove a full spectral theorem for this eigenvalue problem, and we can show that you can fully diagonalize this problem in a Hilbert basis of your H1 space. So yeah, so that's one thing, and as a corollary, this in fact tells you that your regular equation with the funny Robin boundary condition is in fact well posed. It's well posed. Well, it was not obvious at first sight because of this the funny boundary condition. Well, okay, so now it's a classical semi-classical results, which is that when you take the angular frequency going to infinity, you can look at you can use this minimization property, and your eigenvalue goes to the bottom of an asymptotic your asymptotic potential, and the bottom of your asymptotic potential here is at the boundary. So your frequency goes to k squared L squared, and your eigenfunction localizes close to the bottom of your potential. So that's this estimate, which you prove using a so-called Agmon type estimate. Okay, so you're very localized close to infinity. So and okay, so that's nice, because now what you can do is you can do a cutoff. You can cut off this solution in that region, and you can start your regular equation with the initial conditions coming from this cutoff. So this gives you an actual solution of the exact regular equation, not an approximate solution. and the fact that this solution is exponentially small depending on your frequency parameter tells you that the actual solution of the Reggie-Wheeler exact equation remains close to the mode solution for a time which is exponential in L. Okay, so in particular the modes, so the energy of the modes, exact modes, don't decay. So for up to a time t, like exponential of L, you remain strictly bounded from below by some strictly positive constant. Okay, so now if you're okay with, if you want to lose derivative, you can put p angular derivative in the denominator, and if you take L to be like log of t, this gives you that the best decay rate that you can get for this ratio is 1 over log t to a power 2p. So in short, you've shown that the decay rate you have proved is sharp. Okay, so now let me. Okay, so that's something you proved for the Reggie-Wheeler at the level of the Reggie-Wheeler quantities. It's not obvious that there exists solution to the linearized Einstein equation such that which have such Reggie-Wheeler quantities as Reggie-Wheeler quantities. So what we do, okay, I'm going to be brief on this. So there are two options. Okay, so which we both do actually. So one option, first option is actually to exactly integrate the system of the linearized Einstein equation. The second option, which is actually in fact much simpler, is to use the so-called metric reconstruction method, which is a duality argument to construct a solution of linearized gravity from Tokowski solution, but it also works for the Reggie-Wheeler quantities. Well, okay, so two options to do that. Okay, so now let me go to the Kerr-anti-de Sitter case. So 15 minutes. Okay. Including questions. Okay. Okay, so now in the Kerr-anti-de Sitter case, there's a fundamental observation of Hawking areal, which is that if you consider the well-known Hawking vector field, which I denote by K, which is always a Killing vector field. Okay, the Hawking vector field is in the Kerr-anti-de Sitter case globally causal if the following so-called Hawking real bound, so the angular momentum less than the renormalized cosmological constant times the Black-Hawk radius squared, squared. So this bound is satisfied, then the Hawking vector field is globally causal. So note that in the Kerr case, well, this is not the case. I mean, this is the case, but K is equal to 0, so then this never holds. But in the Kerr case, as soon as you've got angular momentum, this Hawking vector field becomes space-like when R is large enough. Okay. Okay. So the fact of having a globally causal Killing vector field gives you that you have a conserved energy which is coercive. Okay, so this fact was used by Holzhegel, Warnick, and Holzhegel and Jacques to show that if the Hawking real bound, if the Hawking real bound is satisfied, then the solutions to the wave equation they are bounded. This is Holzhegel, Warnick, and under some additional assumption, you can prove that same 1 over log decay in time for the wave equation. Okay. A contrario, if your black hole using some argument of Yakov, Schlappentov, Rotman, showed that if your for some black hole there exist black hole parameters which do not satisfy the Hawking real bound, and such that there exists exponentially growing modes, so super radiant instabilities for the wave equation. Okay. Okay. So, question: can we do the same thing for linearized gravity? So first answer is partial answer is provided by a result of Stefan Green, Holland, Ishibashi, and Wald, which Sam's talked about on Tuesday, I think, which is that there's a canonical energy associated to your. There's a canonical energy, and if the Hawking real bound is not satisfied, you can construct initial data such that your canonical energy is strictly negative. And you can also show that this canonical energy decays. So this shows you that these solutions don't decay. Okay, well, it doesn't tell you how it does not decay. So well, that's why I've said it's a partial answer. Okay, so to prove a result for linearized gravity, you want to prove results for the Tucholsky. You want to prove results for the Tucholsky equations. And the Tucholsky equations on the Kerr-anti-de case, they look like this. Okay, and as in the Schwarzschild case, you've got first order derivatives. They were already present in the Schwarzschild case. So you don't have a natural bounded energy for the Tucholsky equations. There's no natural variational problem, as I've showed when you want to construct your quasi modes for the Tucholsky equation. And on top of that, what was working for the Schwarzschild case, the fact that you could commute two times with vector fields and obtain a regular quantity equation. This doesn't work anymore in the rotating case, because the regular equation do not decouple anymore from the other quantities. Okay, so that's basically you can't do anything from of what was done before. So let's try to do the most easy thing that you can do, is to try to look for the existence of mode solutions. So I'm going to look of mode solution, and you can look for real mode solutions, because if you believe in the continuity of the mode frequencies, if you're going to have exponentially growing modes, then at some point they will have to go through the real axis, so they will have to exist at some point purely oscillating modes. Okay, and if you look for purely oscillating modes, you can. It's not a restriction. You can look at fully separated modes in a time radial angular variable like this. Okay, so you're going to try to see if there exists pure mode solutions to the Tucholsky equation on Kerr-ADS with satisfying your coupled ADS boundary conditions. So okay, so our result with Gustav. So we have a mode stability result with Gustav Holzhegel. So the first thing is, so using a classical conservation of the Wronskian type of arguments, you can show that there's the only purely oscillating in time mode solution must actually be stationary. Stationary meaning what? Meaning that the frequency will be the azimuthal frequency times the omega plus, so the same omega plus that was in the Hawking killing thing. So meaning that okay, the Hawking derivative of your Tucholsky quantities must be 0. Okay, so that's one thing. And the other thing, we show that if the Hawking real bound is satisfied, and under some unfortunate technical artificial additional conditions, you can show that there exists no such stationary solutions. Okay. Okay. A contrario, so if you're interested in the existence of unstable mode, so you like to first construct purely oscillating mode. So by the previous theorem, it necessarily is going to be stationary modes with respect to the Hawking vector field. So what the result is the following. So if you take a path of continuous parameter, black hole parameters, such that at one end of the path, your Hawking real bond is satisfied, and at the other end of the path, the Hawking real bond is strictly not satisfied. Then for all azimuthal frequencies sufficiently large, there exist parameters on the path, such that the Tokolsky equations admit non-trivial stationary mode solutions. Okay, and moreover, the Hawking real threshold is critical for that result in the sense that when the azimuthal frequency goes to plus infinity, your black hole parameters will tend to the Hawking real threshold. Okay, so that's the result. Note that in fact you can using metric reconstruction method. I claim that you can prove that there exists there exist metric perturbation associated to these Tokolsky quantities, so actual solutions of the linearized Einstein equations, which are stationary. So this is a result which was already This is a result which was already known in the. There was numerical evidence of this result. And let me just say that then the next step is obviously to try to, from this purely oscillating mode solution, to try to perturb the complex frequency in the upper half plane. So to try to construct from these exponentially growing solutions, non-trivial exploding growing solutions to the Tokolsky equations. And thank you for your attention.
Any questions?
So here the entity dependent correctly. So for small angular momentum, so way below the stability, we still have real mode stability. But in the sense that if you have a real mode solution, then it must be there.
Oh, that's very general. That doesn't requires any bound, neither the Hawking real nor the artificial or artificial.
If you're below the particular bound, can you say something about exponentially growing modes?
If you believe in the continuity of the eigen frequencies, which in fact you can because the functional setting works very well.
Means not with your.
So okay, I didn't get it. So.
That's what the continuity are. Now your modes approach the real axis. There was no motion.
Yes.
So you could imagine some of them coming to the lower half plane.
Yeah, but they have to go through. Okay, but they have to go through the real axis at some very specific eigen frequency, which is the m omega plus. So even if you're super far, at m fixed, if you're super far away on the, but at m fixed you have these modes which asymptote the real line. So at m fixed, the way where you can cross is at a finite distance. So it's yeah. But okay, that's definitely an issue for the analysis.
Other questions? So this last theorem, does it also give you a new proof in the scalar wave case, let's say?
Yes,
Yes. Okay.
but
The result of Dole,
yeah, it does.
Technique, right? Or
It's a different technique. Yeah, because you
Yeah.
can't you can't use the because I mean the idea in Dole's proof and also from Schlappen to Frottmann is that you consider you consider an eigenvalue problem and that eigenvalue problem for the corresponding for the Tokowski equation it has a complex potential, so it's a non-self-adjoint problem, so you can say so yeah, but I mean in the case of in the wave case I would prefer Dole's proof and Chekhov's proof.
Well, if there are no more questions, I thank Olivier for a very nice talk again. And if